One, I am the engineer in Nokia, France. So today I would like to talk about one of our optical use case, which is the dynamic defragmentation in the optical network. Here's the main points of my presentation. First of all, I would like to talk about the toggle software-defined wavelength switch connections, and I could go to why we need the dynamic reconfiguration in the optical network and how we do the defragmentation in optical network, and some of the performance tests that we have done, and also some of the extensions that we have done based on ONOS to enable the defragmentation application. So what we have today, so basically the optical network is mean like when you deploy an optical network, and this an optical channel on line path basically, and when we deploy this optical channel, this optical channel never gonna be changed or reconfiguration or do anything. So for that, we need to really provide a very big guarantee with a very large margin, enable to guarantee the very good quality of service, and also the aging problem. Optical channel can be stay in the network for the few years in advance. And another thing is the deployment of the service in the optical network today takes a month or several months at least. And we are looking for the future. So hopefully in the future, with the software-defined optical network, the future optical network will be defined, try, and continuously adjust the configuration based on the network state and the changing of the network day by day. And the second one is since we can the future optical network provide a programmable, so we can reconfigure the optical network at any time that we want. So we just need to configure our optical channel to work with enough byte to this optical network can stay in the network for a long time, because basically we can monitor the optical network, adjusting, adapting, and make sure that we can guarantee the quality of service on left side. So for example, if we have the optical percent and the utilities, and in the future we can optical network with the advance of the flexible grid, so we can allocate just enough the spectrum resource for the requirement of the network. For example, if we have an application is divided into two main steps. The first one is basically step one. It means you have the current optical channel setting. So you apply that routing and spectrum allocation to calculate to minimize the spectrum occupancy of the current line path setting. Then we have the optimized optical channel setting. And the second step, like you can see in the current optical setting, we have the connection B, and in the optimal one is migrate to the this position of the resource, and it's gonna take the result of the connection A. So for migrate the B to this new position here, basically we need to break A. And another hand is the result in the new the optimized setting, the resource of the optical A gonna take the result of the B. So you have the nerve of the dependency, like B depends on A and A depends on B. So the first step of the second step is to minimize the try to find the the best sequence of the light path migration in order to minimize the subscription time. So the first step, the application gonna calculate based on the current light path setting and the optimized setting to calculate the dependency. So you can see which light path depends on which one, and then from that we apply the minimum feedback vertex set algorithm to build and modify its dependency. Basically, the objective, like you want to break one of the loop, like you need to define the which light path you're gonna apply the make. The break before make. Like usually with the connection, when you apply the make before break, so you don't have the service disbursement time in this case. And once we have the modified dependency graph, you're gonna apply the genetic algorithm, which is a meta-heuristic algorithm to find the best sequence of the optical channel to be migrated. And the network disruption time will be minimized also. We have done application. We did some performance test in terms of the scalability of the application. We did a simulation based on the European network with 28 nodes and 43 links, and we increased the number of the optical channel. So with the 100 optical channel, the application are able to solve the problem, provide the best sequence of light path migration, including the computation time of the current light path setting to the optimized one in 4 seconds. And when we go with the 500 optical channel, is gonna take like almost 100 seconds. I mean 1.5 minutes. So I would like to talk about some extension that we have done based on the ONOS 1.7 to enable the develop the application. So the main part is we have done some OpenFlow extension. We have wrote our drivers enabled to control the Nokia device. This part we're gonna contribute to the back to the ONOS. We have developed the kind of what we call the monitoring intent. So the monitoring intent basically enable the application can subscribe to monitor the whatever optical parameter that he wants. And as I said before, we have developed a zero MQ for subscriber and publisher mechanism. We extend some REST API enabled to control the bandwidth variable transceiver of the Nokia, and we extend a bit on the UI enabled to have the visualization of the optical resource. This is our database. So we build a control plans based on microservices. So the core is the NES Unit controller, which is the very big project inside the Nokia Labs. So the NES Unix controller is mainly based on the ONOS controller, and we did a lot of extension, improvement, enhancement based on the ONOS. And on top of the controller, we have defined and developed a set of the optical application. For example, we have the routing and spectrum assignment application, the defragmentation application, the restoration, the protection, and the QT monitoring application. So this one already saw in the ECOP conference in 2016. That's one we have saw is in the OFC conference last year in LAs. And we for for the server protocol, we are using the OpenFlow protocol, and we most of the extension have done based on the link OE, and we also integrated our let's say hardware driver inside the link OE and make the link with the OpenFlow inside the link OE. So basically, the controller can control really our hardware through the link OE. And so now I'm gonna talk about a little bit about some of OpenFlow extension that we have done. So we all know that the current ONOS, I think the latest one doesn't support OpenFlow 1.5. Not yet. The latest, okay, yeah. So most of the work that we have done is based on ONOS 1.7. So at this moment, basically it doesn't support the 1.5. So even with the 1.5, we have multi-flow mode message to configure layer 0 table, but basically you only configure the filter and the optical switch. It means you just configure switch bars, but it doesn't enable you to configure the BPT or the bandwidth variable, which is the source of the optical connection, or the destination, which is the receiver. And the pop message that you can configure the text power and the central frequency. Some of the statistics messages allow you to receive the monitoring information like text power, ice power, transmitter power, receiver power, temperature, bias current, and all the monitoring parameters result as one. So it means when you send one request and you will receive all of this information. It doesn't allow you to filter